Hello again. Today we're going to continue talking about identities, specifically some identities that are called the sum and difference of angles identities. So we've been using identities to find values. We've been simplifying expressions with identities, and in the last section we verified identities as well. So in this section we're going to continue to find values using sum and difference identities. And we're going to continue to verify trig identities, but this time again using sum and difference identities. So why is this important? Sometimes, for example, when you're using your Wi-Fi, your signal might temporarily be lost. Waves that pass through the same place at the same time can sometimes interfere with each other. And interference happens when two waves combine or add together to have a greater or a smaller amplitude. And so sometimes when you have internet interference, what's happening is that two waves are being added or subtracted together. And that's an example of when we could use or apply or model something with sum and difference identities. So in this equation up here that it was giving me for one of these curves, notice that I have an addition of angles inside of here, right? It's sometimes helpful to use formulas for the difference or sum of two angles. For example, and this is something that we're going to do specifically, the sine of 15 degrees. If I want to do that by hand, 15 degrees is not one of the angles on the unit circle that we know how to do by hand. But I can rewrite 15 degrees as two common angles that are on the unit circle that I know about. 60 degrees and 45 degrees. So 60 degrees minus 45 degrees is 15 degrees. And we're going to use the identities below to be able to do these kind of things by hand because I know something about sine and cosine of 60. Same thing with 45. So here are the identities. You do not have to memorize these, but you do need to be able to use them. So the sum identities say that the sign of a sum, remember, you cannot, not distribute sign. Sign is not a number, sign is a function. This means the function of this sum. But there is an identity that if I need to rewrite it, because let's say I need to solve for one of these, but I can't get it out of the parentheses, I can rewrite it like this. The sine of A times the cosine of B plus the cosine of A times the sine of B. So these are equivalent expressions. Same thing with the cosine of a sum. It's the cosine of A times the cosine of B minus the sine of A times the sine of B. And then the tangent one looks a little more complicated, but the tangent of A plus B is the tangent of A plus the tangent of B over 1 minus the tangent of A times the tangent of B. And then you guys can pause for a second and look at the difference identities, but basically we're just going to be applying these in different situations. So for example, we're going to find the exact value of the sine of 75 degrees. Again, this is not a value that is on the unit circle that we know something about. 75 degrees, we can't get it from a special right triangle. Its reference angle is 75 degrees. We can't do anything with that by hand. So we're going to rewrite this 75 degrees as a sum. So look at what angles they choose here. I need to figure out, okay, what common angles, what angles from the unit circle can I use to rewrite 75 degrees? So in this case, you should notice that the sine of 75 degrees is the same as 30 degrees plus 45 degrees, right? 30 plus 45 is 75, so these are equivalent expressions. Now we're going to use our sum of angles formula. So the sine of alpha plus beta, or A plus B, is the sine of A times the cosine of B plus the cosine of A times the sine of B. So in this case, this is like my alpha, and this is like my beta. So I'm just applying the formula, just plugging it in. And now, these are all things you should know off the top of your head. You will not be using a calculator for these. The sine of 30 degrees is 1/2. The cosine of 45 degrees is square root of 2 over 2, plus the cosine of 30 is square root of 3 over 2, and the sine of 45 degrees is square root of 2 over 2. So then I'm going to multiply this and get square root of 2 over 4 plus the square root of 6 over 4. And then I just rewrite those as a single fraction, and that is my final answer. So the sine of 75 degrees is equal to the square root of 2 plus the square root of 6 all over 4. Sometimes they might give you a negative angle. Again, negative 75 degrees. Its reference angle is still 75 degrees. That's not from any of my special right triangles. So to do this by hand, I'm going to need to use an identity. So in this case, they're going to use a subtraction identity because, and again, I need to figure out how to rewrite negative 75 degrees using common angles from my unit circle. So in this case, 75 degrees is 60 degrees minus 135 degrees. Both of those are common angles from the unit circle. So I'm going to use this identity that they give you up here. The cosine of a difference is the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. This is my alpha, 60 degrees. 135 degrees is my beta, and we just plug into our formula. And again, cosine of 60 is 1/2. Cosine of 135 is negative square root of 2 over 2 because it's in the second quadrant, and that's where cosine is negative. Sine of 60 degrees is square root of 3 over 2, and the sine of 135 degrees is square root of 2 over 2. So then I just multiply and simplify. Write it as a single fraction, and that would be your final answer. All right, try this one. The exact value of the sine of 105 degrees. Your answer should be A. Let me show you the work. There's the work for how you would do that. Notice I rewrote 105 degrees as 60 degrees plus 45 degrees and then used my identity. Okay, so try one with a negative angle here. The answer to this one should be D, negative 1/2, and I'll show you the work. All right, there's the work for that one. Again, notice I'm using the subtraction identity, but be careful with your formulas. The subtraction identity for cosine actually ends up adding when you write it out with the formula. Then I got all of my values, multiplied, and simplified. Okay, take a look at this example. A geologist measures the angle between one side of a rectangular lot and the line from her position to the opposite corner of the lot as 30 degrees. So that's this 30-degree angle here on our picture. She measures the angle between that line, so this line that we drew here, and the line to the point on the property where the river crosses. So this angle is 45 degrees. If Z is the distance between the upper left corner of the property, so my property is this rectangle, and the point where the river crosses the top boundary, so where the river crosses my boundary line here, then this relationship is true. The tangent of 15 degrees equals Z over 50. Right? Or another way to rewrite that, instead of using 15 degrees, would be the tangent of 45 degrees minus 30 degrees equals Z over 50. So here we're going to use the identity that I know for tangent to find an exact value. And we're going to solve for Z. So here's my original equation that they gave me. And this, they are applying the identity, which you should see in the chart at the beginning of your notes. And here they're just filling in the values. 1 minus 1 over the square root of 3. 1 plus 1 times 1 over the square root of 3 equals Z over 50. And then what they did is they multiplied both sides of my equation by 50 so that I could get Z by itself. And here we're just simplifying. So we're taking this and we're multiplying by the conjugate of my denominator in the numerator here. Oops, there, I'll put that there. And numerator and denominator. So we're simplifying this. So here is what we get after we multiply by that in the numerator and the denominator. What I did in the numerator is I foiled 1 minus 1 over square root of 3 times 1 minus 1 over the square root of 3. Same in the denominator, and I end up with this. Notice I'm just leaving my 50 out in front for now. Then I simplified 1 plus 1/3 is 4/3, 1 minus 1/3 is 2/3. And then dividing by a fraction is the same as multiplying by its reciprocal. So I'll take 3/2 times 50 times 4/3 minus, and I'm going to go ahead and simplify that second fraction so I don't have a radical in the denominator. equal to z. 3/2 times 50 is 75, because 50 divided by 2 is 25. 25 times 3 is 75. Times 4/3 minus 2 square root of 3 over 3. And then when I distribute the 75, 75 times 4/3 is 100. Sorry, I'm running out of space. And 75 times negative 2 square root of 3 over 3 is negative 50 times the square root of 3 equal to z. And that's what we have on the next page as our final answer. All right, and one way to check would be to take what we got as our answer to find the arctangent of it and see if it gives me 15 degrees. All right, you guys try this one. I'm going to stay here for a second to let you read it, although it's also on your note guide, and then you try the next one. Okay, your answer here should be A. In this case, we had a simpler identity to use than the tangent one. So you should have had the sine of 45 degrees minus 30 degrees is equal to the sine of 45 degrees times the cosine of 30 degrees minus the cosine of 45 degrees times the sine of 30 degrees. And then just fill in your values and simplify. All right, the last part of this section is to verify trig identities. So we're going to verify that this equation is actually an identity. So what we do here to start is I notice here I have subtraction inside of a cosine, right? I have the cosine of the quantity of two angles being subtracted. So again, my little question mark, because I'm verifying, I'm proving. Notice I rewrite my left side using the cosine subtraction identity. So that's the second one in the difference identities side of your chart at the beginning of notes. And then I fill in what I know. The cosine of 360 degrees is 1. Cosine of theta I don't know because I don't know what theta is. The sine of 360 degrees is 0. Don't know the sine of theta. But I'm asking, does this equal cosine of theta? And it does, because 0 times the sine of theta is just 0. Then I have 1 times cosine of theta, so I have proved or verified that identity. We're going to do the same thing here. I have another subtraction identity. There's my original equation, notice with my question mark. Use the difference identity, cosine of pi times cosine of theta plus sine of pi times sine of theta. The cosine of pi is negative 1. The sine of pi is 0, so 0 times the sine of theta goes away to 0, and I'm left with the correct equivalence. Negative cosine of theta equals negative cosine of theta. Okay, so you guys get to try this one. All right, it turns out that this one should be an identity. This is how you would start. The cosine of 90 times the cosine of theta minus the sine of 90 degrees times the sine of theta. And then you end up with the cosine of 90 degrees, which is 0. So I have 0 times the cosine of theta minus 1, which is the sine of 90, times the sine of theta. I'm asking, does that equal negative sine of theta? And you can see that since 0 times cosine is just 0, I'm left with negative sine of theta does indeed equal negative sine of theta. All right, one more, last one. All right, your answer here is B. This one is also an identity. They're showing you here what your first step would be. We would put our question mark. And then the sine of 180 degrees is 0. So I have 0 times the cosine of theta. Then the cosine of 180 degrees is negative 1 times the sine of theta. I'm asking, does that equal negative sine of theta? And because 0 times cosine of theta is just 0, I do end up with negative sine of theta is equal to negative sine of theta. All right, that's the end of this section. Again, you don't have to memorize the identities, but you do need to be able to use them.